I'm Zach Murez. I'm presenting our work on learning to see through turbulent water. My co-authors are Zhengqin Li, David Kriegman, Ravi Ramamoorthi, and Manmohan Chandraker. So the problem we're attacking is imaging through dynamic refraction. Here we have a camera in one medium, imaging a scene in another medium. And because of this, they're separated by a refractive interface where light will be bent depending on the surface normal, which is random and unknown. So some examples of this are when you're looking down into water. It also occurs when you're looking through the atmosphere. So beyond consumer photography, some applications of this would be quickly mapping coral reefs using a drone, whereas currently oceanographers have to swim around and take pictures underwater. Another application could be a periscopeless submarine. But these works, as well as all other previous work, has assumed multiple images as input, often a high-speed video, whereas we attack the problem of single image restoration. So a baseline naive approach, we could just apply the image-to-image translation framework of Isola et al. However, when we did this, we found that it wasn't able to handle the large geometric distortions that occur in this case. So instead, we chose to train a two-stage network. First, we have a warp net that takes in the distorted image and outputs a two-channel warping field. This warping field is then applied to the distorted image to undistort the geometric distortion. However, this can't handle blur as well as non-invertible warpings and other such things. And so we have a second network that is a color network that takes in pixels and outputs pixels. And this can fix those problems that were left behind. Now we note that to train this, we don't actually need ground truth warping fields because the warping is applied differentiably, and so we can train the whole thing end to end. But we do need distorted and undistorted image pairs. And no such data set exists, so we created our own. To do this, we put a camera on a tripod looking down into a glass tank that was full of water. We have two pumps in there that keep the water turbulent, and a computer monitor which we show ImageNet image on. And so we're able to, over the course of a couple days, collect around 100,000 images. So here's a diagram of our setup, an example original ImageNet image as well as the distorted image. So to train this, we used the L1 reconstruction loss. We also added an adversarial discriminator to help reduce blur and make the images look more realistic. We also used a perceptual loss to force the network to preserve details as well. Here are some examples on results on monitor images from a held out test set. On the left, you can see the input image. The next column is the result of just using the color net, which is equivalent to the image-to-image translation. The next column is the full network, but only trained with L1 loss. So here the results are still blurry. And then our full network with the L1 and the adversarial loss and ground truth. But then the question is, how well does this generalize to real objects, not to images of monitors? And so we captured some objects out in the real world, like a fountain. Here's an example of a toy fire truck. And on the left, you can see the input image. On the bottom, you can see zoom in insets. And you can see the writing and the structure of the ladder has been all warped and distorted. And you can see that using Isola's image-to-image translation alone doesn't really correct the geometric distortions, whereas ours is able to correct the geometric distortions, and it looks a lot better. So, thank you.